Now it is your turn to write some code. In these labs, you will build and stress the dynamic array and see one reminder. Every heap block your code owns, you must free. This is Lab 1. Your goal is to build the whole dynamic array in C from start to finish. Take your time. You have about 30 minutes. This is the API you will implement. There is vec init to set up an empty vector. There is vec append to add a value at the end. There are vec get and vec set to read and write a slot. There are vec insert and vec delete for the middle, and there is vec free to give the block back. The most important one is vec append. When the block is full, it must double the capacity from 0 to 1 to 2 to 4 and so on. Use realloc and use the safe temporary pointer pattern, and vec free must release the block. To test it, append 10, 20, 30, and 40 and watch the capacity climb 1, 2, 4. Then insert 55 at index 1. Then delete index 0. After a set of 99 in the middle, you should see the values 55, 99, 30, 40. Predict before you run. After you append 4 values into a fresh vector, what is the capacity? Take a moment. The answer is 4. It doubled from 0 to 1 to 2 to 4, and the fourth append fit. And never assign realloc straight back onto v-arrow data. Let's look at one solution. Try your own version first, then compare it with this one line by line. Look at vec append. The first thing it does is check for full. Is size equal to capacity? If yes, there is no spare slot, so we must grow first. This line picks the new capacity. If the old capacity is not 0, we double it. If it is 0, we start at 1. So the growth is 1, 2, 4, 8, and so on. Now we call realloc for the new capacity, and we store the answer in a temporary pointer called temp. We do not touch v-arrow data yet. This is the safe check. If temp is null, realloc failed. We return -1 and the vector is still whole because we never change the old pointer. Only on success do we repoint. We set v-arrow data to temp, and we save the new capacity. Now the vector points at the bigger block. After the check, there is always room. This line writes x into the next free slot, and then adds 1 to size in the same step. Now vec insert. Notice the clever trick. It first calls vec append with a value. That guarantees there is room and it grows the block if needed. Then this loop shifts elements to the right, 1 slot each, to open a gap at index I after the shift. We drop the new value into that gap. Insert is big O of n because of the shift. Vec delete does the opposite of insert. This loop copies each element 1 slot to the left, over the whole left by the removed value. Then we lower size by 1. The array is now 1 element shorter. Delete is big O of n because of the shift. Finally vec free. It calls free on the block, sets the data pointer to null, and resets size and capacity to 0. That is 1 free for the whole vector. This is lab 2. So far the vector only grows. Now you will make the capacity shrink too. A vector that grew huge and then got small should hand the memory back. Your job is to add one function, vec pop. It removes the last element. After removing, if the size falls below capacity divided by 4, you have the block with realloc. To test it, grow the vector to 16, then pop everything. Each time the block shrinks, print the new capacity so you can watch it fall. Predict before you run. Why shrink below capacity divided by 4 and not capacity divided by 2? Take a moment to think. Here is why. If you have right at the half full line, a push then a pop on that line makes the block grow, shrink on every call. The 1/4 gap gives you a safe margin, so the average cost stays big O of 1, and never shrink below capacity 1. Let's look at one solution for vec pop. Try your own first, then follow along with this one. First, a guard. If size is 0, there is nothing to pop, so we return -1 right away. This keeps the function safe even if the caller forgets to check. We drop the last element. We just lower size by 1. The value is now outside the used part of the array. Now the shrink test. If the capacity is bigger than 1 and the size is now less than capacity divided by 4, the block is too empty. Time to shrink, which we do on the next slide. When the block is sparse, we shrink it. Here is the safe way to do that. We pick a new capacity, which is the old capacity divided by 2, so we have the block. We call realloc for the smaller size, and we store the answer in a temporary pointer, temp. This is the safe move again. We only act when temp is good. Then we repoint data, save the new capacity, and print the shrink line. If realloc failed, we keep the bigger block and print nothing, so we never claim a shrink that did not happen. Now let's run it and read the output. Look at the output. We grew to 16, then popped everything. The block shrank at size 3, at size 1, and at size 0. The 1/4 rule makes these shrinks rare, so pop stays amortized big O of 1. This is lab 3. Earlier we argued that append is cheap on average. Now you will measure it and see the numbers with your own eyes. Start with an empty vector and append 16 values. On each resize, print the old capacity and the new capacity, and print how many elements were copied. Add all the copies into a running total. At the end, print the total number of copies. Then check that it is under 2 and here n is 16, so 2n is 32. Predict before you run. For n equals 16, at which append numbers do the resizes fire, and what is the total copy count? Take a moment. Here is the answer. The resizes fire on appends 1, 2, 3, 5, and 9. The copy counts are 0, 1, 2, 4, and 8. Add them up. 0 plus 1 plus 2 plus 4 plus 8, which is 15. 15 is well under 32. And remember, one resize copies exactly the current size. Let's look at one solution. It is the append loop with printing added, so we can count the work. Inside the loop, we check for full. If size equals capacity, this push forces a resize before we can write. We do the resize on the next slide. After any resize, there is room, so this line writes the value into the next slot and bumps size by 1. At the end, we print the total copies and compare it with 2n. Here is the resize done safely. This runs inside the loop when the vector is full. We pick the new capacity by doubling. If the old capacity is 0, we start at 1. We realloc for the new capacity, and we store the answer in a temporary pointer called temp. We do not touch v.data yet. This is the safe check. If temp is null, realloc failed. We free the old block and return one, so we never leak memory and never lose the block. Only on success do we repoint. We set v.data to temp, so the vector now points at the bigger block. This is the instrument. On each resize, we print the old capacity, the new capacity, and how many elements we just copied. And this line is the count that matters. We add the current size to the total copies, because a resize copies exactly the current size. Now let's run it and read the output. Look at the output. The copies are 0, 1, 2, 4, and 8, the same powers of 2 we saw on the plot. Their sum is 15, which is less than 2 times 16, which is 32. That geometric total is why each append averages a constant.